Welcome to the first topic of Module 6, Fire Debris Examinations. We will begin by discussing the components necessary for fire to initiate and to be sustained. We will also discuss the signs of an accelerant-initiated fire and the proper ways to collect and package fire debris evidence. Finally, we will discuss the various laboratory techniques used in accelerant examinations. Arson is one of the more complex and difficult crimes to investigate due to the fact that the perpetrator has planned the act, is usually not present during the act, and the destruction is so extensive at the crime scene. So it is very important for the forensic scientist to be able to detect and identify any relevant chemical materials collected from the crime scene that are going to assist in the reconstruction of identifying igniters and also detonating mechanisms. If we initially talk about fire and define fire, it is a rapid and sustained oxidation process with the evolution of light and heat at varying intensities. So fire is going to involve an oxidation reaction, combustion, and some form of heat transfer. This is usually done by the oxidation reaction involving a fuel and oxygen. When these combine, combustion occurs, giving off energy in the form of heat and light. We can think about fire as having four specific requirements: an oxidizing agent, a fuel, an ignition source, and also the capability of having a chemical chain reaction. In most instances, the oxidizing agent is going to be oxygen. However, there are also some chemical oxidizers that can be used in a fire. For fuels, this is going to be the substance that reacts with the oxidizer, and they can be either solid, liquid, or gas, which we will discuss shortly. Most of the common fuels are going to be hydrocarbons. However, there are a few terms that we need to discuss: vapor pressure, flash point, auto-ignition temperature, and flammability limits before we discuss the various fuels. So, exactly what is vapor pressure and some of these other terms? Most of these you may have heard in general chemistry. Vapor pressure occurs when chemicals are exposed to air and they will evaporate. However, in a closed container, a vapor pressure will occur where the chemical will reach a point where it stops evaporating. The pressure of the gas has built up to the point where there is no more exchange into the air. Vapor pressure is the pressure exerted by a gas in equilibrium with a solid or liquid in a closed container. A sample that has a very high vapor pressure is going to be referred to as being very, very volatile. The higher the vapor pressure of a liquid at a given temperature, the higher the volatility or evaporated liquid in air. And this relates to the flash point of the chemical. The flash point is the lowest temperature at which a substance will give off a vapor that will flash or burn when ignited. An auto-ignition temperature is the minimum temperature to which a substance must be heated in air to ignite independently of a heating source. And we also talk about flammability limits. The flammability limits are the lower and upper concentrations, usually of a substance in air, between which combustion will be supported. So you can see from this example the yellow or orange range is actually the flammable range. There is a lower limit and an upper limit. Below the lower limit, there is not enough fuel to sustain the flammable range. Above that, there is too much fuel. So the lower flammable limit is going to have more air than gas or vapor present, and your upper flammable limit is going to have more gas or vapor than air. Chemicals will have various flammable limits, and you can see this from the chart contained in this slide. A very good example to show the application of flammability limits is on this slide shown with ethylene. Ethylene has a low explosive limit of 2.7 and an upper limit of 36%. Therefore, in the presence of an ignition source, if the concentration of the gas is less than 2.7 or greater than 36%, there is no risk of explosion. However, if the concentration of the substance is between these two limits, the mixture could explode. So now that we know some of the common terms in reference to fuels, let's talk a little bit about the common fuels. We said that there could either be solid, gas, or liquid fuels. The most common solid fuel is going to be coal or charcoal. However, there are mixtures such as black powder, flash powder, matches, and safety flares that are also considered solid fuels. These fuels will burn by direct combination of oxygen with the surface. There are also several metals that are also very reactive and can be considered solid fuels. There are also several gases that, when mixed with the proper amounts of air, can also be ignited. But most of the time, what we see in forensic examinations are various types of liquid fuels, so that the vapors of the liquid fuels actually support the flame. The most common of these is going to be your petroleum-based chemicals, things such as gasoline, lubricating oils, diesel, and kerosene. So in addition to the oxidizing agent in the fuel, we must also have an ignition source. This can come from a variety of items, either natural, accidental, or intentional. The natural ignition sources could be chemical reactions that get a little bit out of control, or lightning, or the spontaneous combustion of materials. There's a lot of times accidental ignition sources, so heaters or appliances that have faults that occur, chimney fires or fireplaces, electrical wiring or lighting that have problems, and also trash and campfires would be considered accidental. However, another ignition source can be intentional. This can either be conducted through the use of matches or lighters, or in many instances with ignitable liquids and considered arson. The final requirement for fire is the fact that there must be the chemical chain reaction that occurs. Combustion is the chemical reaction between the oxidizer and the fuel that have been ignited through that ignition source. This feeds a fire more heat and allows it to continue while the supply of the oxidizer and the fuel are still present. So now that a fire has occurred, we have to concentrate on the detection of any evidence that might be able to be retrieved from that fire scene. Usually this is going to be a combination of a good visual search and then combined with some of the alternative methods. And this will provide the best alternatives for the detection of specific fire debris samples that would be examined for any ignitable liquids. So if we begin by a good visual search, this is going to consist of looking for any burn patterns or pour patterns if there have been ignitable liquids there at the scene. You want to try to concentrate to find the origin of the fire. And then samples should be taken within this area and also at the edge of a pour pattern if it is present. To get the best results from the analysis, the fire debris, if possible, should be collected from absorbent or porous materials. So this is going to be things such as carpeting, charred wood, rags, insulation or paper, things like this that can actually absorb more of that ignitable liquid. In a lot of instances, there might also be the possibility of collection of samples from protected areas. So any joints, cracks, or seams that may still have some of the ignitable liquid present. You want to steer clear of deeply charred areas, ashed areas, or completely burned areas, because most likely if there had been an ignitable liquid present, it's going to have been consumed in the fire and a lot harder to detect. Also, non-porous materials aren't going to have absorbed a lot of that ignitable liquid. Another thing to consider is areas where there have been major amounts of water added in the suppression of that fire. This would only dilute anything that you might be trying to identify. In addition to the visual searches, a lot of times canines will also be used to search a fire scene. The dog's sense of smell is 200 times greater than the human nose, and many dogs have been trained to specifically sniff out very small trace amounts of accelerants. There's also several electronic devices that can be used, electronic sniffers, that are more or less like a portable gas chromatograph with a mass spec attached. However, when using these type of instruments, it doesn't confine it to a small area. So it's going to give you more of a general area where that saturation may have occurred. Also, sniffers are only effective for approximately 2 to 3 days after the liquid has been added to the scene. There's also the possibility of using visual indicators, which are more of an atmospheric type sampling, and these are based on a color test. Most recently, alternate light sources have been used at fire scenes. It has been documented that some hydrocarbons will fluoresce when exposed to ultraviolet light. So the use of an alternate light source might assist in finding different pour patterns. So now that you know a little bit about how to isolate the areas where you might want to collect samples from, we should concentrate on the collection and the storage of the actual evidence. It's very important with fire debris samples to choose containers that are going to be non-porous and vapor tight. Remember, a lot of the ignitable liquids are going to be very volatile, so you have to make sure that after the collection that your sample doesn't evaporate before the analyst has an opportunity to do their examination. You also have to use containers that are going to be non-contaminating. This comes into play with some of the glass jars that can be used to collect samples. You need to make sure that the lids do not contain items that might contaminate your ignitable liquid that could be present. Jars that have rubber seals might interfere with the analyst interpretation. So if necessary to use a jar that has a rubber seal, if you put a layer of foil in between the jar and the lid, this will allow no contamination to occur from that rubber seal. In most instances, paint cans are going to be the containers that are chosen for fire debris samples. These containers are vapor tight. The cans should only be filled partially full. So if you're using a 1-gallon can, you want to leave a little bit of airspace in the top of that can. So leave about 2 inches empty at the top of the can. There are some specialized plastic bags that can be used for fire debris, but you need to make sure that these are the specialized plastic bags, not just ordinary plastic bags. Liquids can be contained in a jar, and that's what, if questionable, always put that layer of foil in between the jar and the lid itself. It's also important when you're at a fire scene to make sure, in addition to any fire debris, that you collect control samples. There are some substances that might burn at a crime scene that may actually produce hydrocarbons and interfere with the interpretation of the analyst's data. So to counteract this, if you collect control samples, they will know the possibility of these interfering hydrocarbons. So if for some reason you're collecting samples from an area of carpet that has actually been burned, you also want to, if possible, collect a small amount of the carpet that has not been burned as your control sample. Other things such as cleaning agents, pesticides, roofing materials, all of these things might interfere with that analyst interpretations. So if all possible, always try to collect control samples. Another thing to consider is if there are individuals there at the scene that you think could potentially be your suspect, you might want to go ahead and collect their clothing, because a lot of times in the commission of the crime, if they are pouring ignitable liquids, some of those may have splashed on their shirts, jackets, pants, or shoes. Always remember to label your containers prior to packaging, and when necessary, remember to attach the appropriate labels for that sample. Once again, always make sure that your packages are sealed with tape. This provides a security measure. And then, in the instance of fire debris samples, you have to be very careful with how you're getting your samples to the laboratory. If it is necessary to be mailed, the fire debris can actually be mailed certified mail. However, if there are flammable liquids that you're wanting to get to the laboratory, you have to use either Federal Express or the UPS service. And these items must be clearly marked as the possibility of flammable contents. So now if we begin to discuss the examination of fire debris, we initially want to know what actually can we learn from this examination. First of all, we're going to try to identify if there is an ignitable liquid present. And then we're going to try to identify that class of ignitable liquid, and in some situations, possibly identify the ignitable liquid. There are several different techniques that can be used to isolate the ignitable liquid from fire debris. The first of these is solvent extraction. And this more or less involves applying a solvent to the fire debris sample. Usually the solvent that's going to be used is carbon disulfide or pentane, and these are actually poured over the fire debris itself. The solvent is collected, and then this is what would be analyzed for your ignitable liquid. This can be particularly useful when you're trying to extract ignitable liquids out of non-porous substances. It's also very useful for the retrievable when you have extremely small sample size. However, the one thing that you have to be concerned about is that your solvent may be extracting more than just your ignitable liquid. So the analyst has to be aware of this and very carefully interpret the data that they receive. Another method that's commonly used for isolating ignitable liquids is headspace vapor analysis. This traps the volatile portions in the container itself, allowing the gases to be injected into an instrument. This is very useful for some of the volatile compounds, such as alcohols and lacquer thinners. However, this technique is not used as often as passive headspace because it is less sensitive. This method does allow for duplicate testing, and most laboratories require duplicate testing for arson debris samples. But most laboratories will conduct their analysis by using passive headspace analysis. This is where small strips of activated charcoal are suspended in the headspace of the container itself. The containers are heated, causing the vapors to be trapped onto the charcoal strip. Then the charcoal strip is extracted with an organic solvent, and this is actually then what is tested on a gas chromatograph with a mass spectrometer. This technique is very sensitive for isolating ignitable liquids out of fire debris, and it is the most commonly used technique. Most often it's D-flex strips that are used, and it does give very good recovery. So once you've isolated the ignitable liquid or possible ignitable liquid out of the fire debris, we're going to use a gas chromatograph with a mass spectrometer to identify the ignitable liquid. This is one of the instruments that we discussed in the instrumental methods lecture. It's going to provide two different forms of data. The first being the chromatogram, which is shown at the top right-hand portion of the microscope slide. And it's going to give you very characteristic patterns for the various ignitable liquids. But then, in addition to the chromatogram given by the gas chromatograph, you also obtain the ion spectra from the mass spectrometer. Currently, ignitable liquids are going to be classified into several different categories, and then whether or not it's a light mixture, medium, or heavy substance. So you can see from this a lot of the common petroleum products or ignitable liquids and the various headings that might be included in a laboratory report. However, keep in mind once again that it is very necessary to try to obtain known samples when in your collection of the fire debris. This helps that forensic scientists eliminate the common interferences that might be seen with the extraction of the ignitable liquid. So once again, many plastics and polymers and also many household products might contain petroleum distillates, which could be inferred as an ignitable liquid. When a complete examination is performed, the analyst could reach several different conclusions. If the sample does not display the features necessary for an identification, they would clearly say that an ignitable liquid was not identified. This does not necessarily mean that one could not have been present. It's just that the analyst was not able to identify the ignitable liquid. If a sample's chromatogram displays all of the features required for the class identification, the report may say very simply that it does contain a petroleum distillate, and then examples are normally given for that category. In some instances, the sample may be found to contain a mixture. So the wording may contain that, saying that the exhibit contained light and heavy petroleum distillates, and then examples would be given for both of these classes. And likewise, in some instances, the peaks in the chromatograms may spread straddling between different ranges. So once again, the report may say that it contains a light to medium petroleum distillate. This concludes our discussion on fire debris.